Finally, let us address the subject of the power spectrum of large-scale structure. You may recall that we introduced this concept when we talked about primordial density field. And now, just like then, some familiarity with Fourier analysis is absolutely essential. So if you are familiar with Fourier analysis, the main subject of today's lecture will be almost trivial. And if you're not, it'll make no sense whatsoever. So this will be like a really good time to refresh your knowledge of Fourier analysis. Done? Okay, but that was fast. So let's get going. So we can characterize the density field of large-scale structure in the same way as we did before. So let's take its Fourier transform. Here is the formula. It's essentially almost the definition of Fourier transforms. And the inverse transform is given by this. So in this way, spatial scales and wave numbers k are connected. And the power spectrum of density fluctuation is obviously a complex product of spectrum by itself. Now recall what was the value of two-point correlation function expressed from the density field, the expectation value of it. In other words, this is exactly what it is. So correlation function is a transform of the power spectrum. Power spectrum and correlation function are a Fourier pair. They're completely equivalent to each other mathematically. And here is an example of what they look like from Las Campanas redshift survey that you may recall. What's shown here is both three-dimensional two-point correlation function and power spectrum corresponding to the same large-scale structure. You may recall that two-point correlation function was fairly easy to evaluate in any one of several ways. But power spectrum is really what theory produces. So one can be translated into the other. Now we usually express the power spectrum on a log-log axis, and theoretical models fitted against observations give us the shape of it. However, the amplitude has not been defined. There are two ways in which that can be done. One is to measure fluctuations of the density field at a particular scale. And typically, a sphere of radius of 8 h to the minus 1 megaparsecs is used because that gives the RMS of fluctuations close to unity. Turns out it's a little less than that for moderate measurements, but traditionally 8 megaparsecs is used. So whatever the value of that is, gives us unit normalization of the power spectrum at that spatial scale. Well, essentially what's been done here is you're convolving what's technically called a spherical top hat filter, but it's really nothing but a sphere with the power spectrum itself. An alternative way is to simply use observations of cosmic microwave background, which give us power spectrum on very large scales. So if you have a model like cold dark matter model, you can fit it on those scales, evolve for the appropriate linear growth of fluctuations, and that works just as well. So here is one of the modern renderings of the power spectrum of large-scale structures, spanning the range all the way from super horizon sizes down to the scales of galaxies. The plot assembles several different kinds of measurements. They're all brought to the same redshift by scaling in linear regime. At large scales, cosmic microwave background is what's done. That overlaps with measurements of clustering from large-scale structure from redshift surveys and such. And then going on to smaller scales, we use things like abundance of clusters of galaxies. That's essentially statistics of high-density peaks. And clustering of Lyman alpha clouds, which are subgalactic fragments. And weak gravitational lensing reflects the density distribution of the dark matter, and so that too can be used to probe distribution of CDM on intermediate scales. And the line going through the points is the standard cold dark matter model. As you can see, it's a remarkable good fit and also an excellent agreement between these completely different ways of observing it in the regions where they overlap. So this gives us a real confidence that we actually know at some level of certainty what's going on, and that one of the major reasons why people believe that the CDM model is the correct one. Just as an aside, you may recall baryonic acoustic oscillations. And this is actually how they were detected. by looking at the two-point correlation function or power spectrum at scales in the vicinity of 100 megaparsecs. So this is an absolutely essential use of this concept as a cosmological test that can be used to improve our knowledge of cosmological parameters. So far, we talked about power spectrum, that is the distribution of amplitudes of density fluctuations. But in that process, as in computing power spectrum, we completely neglect phase information. Now, here is a dramatic illustration of why phase information is important, produced by Alex Zale. And it's a toy model, the density model that is really Voronoi foam, kind of mimicking the filamentary structure that we see in large-scale structure. What was done here, its Fourier transform was taken, and then the phases were randomly scrambled, leaving the power spectrum identical. Then transform back with scrambled phases, and you see the plot on the bottom. It looks like a complete noise. The coherence is completely gone. So whereas the distribution of fluctuations is the same, their arrangement is completely different. The phase coherence is being lost in this computation. And obviously, we have to somehow learn how to use statistics of the phases of the density field power spectrum, or rather Fourier spectrum, in order to characterize it fully. Because when you look at large-scale structure, you don't see just a lumpy density field. You do see a mesh of filaments and voids and whatnot. Amazingly enough, so far, nobody has come up with a really simple, elegant, complete way of describing this. So maybe you will. So we discussed clustering of galaxies at some detail, but what about clustering of clusters of galaxies? Or in fact, you can discuss clustering of any elements of large-scale structure, galaxies, groups, clusters, superclusters, and so on. As it turns out, clusters also cluster, and their clustering is stronger than that of galaxies. Actually, there is an excellent correlation between the strength of clustering, say measured through clustering length, and the richness of the system at which you're looking. The richer clusters are clustered more strongly. This is actually a very interesting result, and at first it was puzzling why should that be so, until Nick Kaiser came up with the explanation that this is due to a phenomenon now called biasing. You can consider density field, and so there are some high peaks and low peaks. Remember, it can be also decomposed in waves of large wavelength and small wavelength fluctuations riding atop of large waves. So if you impose a threshold for a formation of certain kind of objects, say 5 sigma cut, then the highest peaks will be strongly clustered because the smaller fluctuations are carried together by the large waves, and those that happen to be at the crest of a big wave will be all clumped together. This is in the same sense as if you were to ask, what are the highest points on the surface of planet Earth? And if you put a cut at a few kilometers elevation above the sea level, you'll see they're very strongly clustered where the high mountains are, say Himalayas and Cordilleras and so on. Whereas if you lower down the threshold to the ground level, then everything will be more or less uniformly distributed. So this is a simple explanation that the highest density peaks always cluster more strongly than the lower density peaks. And this applies to galaxies as well. We find out that denser galaxies, elliptical galaxies say, cluster more strongly than spiral galaxies. And I've shown you a plot of that we've seen earlier. This is the explanation why. It also has some implications. The highest density peaks will be the first ones to form at small scales. We'll come back to this phenomenon when we talk about galaxy formation and evolution. So let us recap everything we learned about large-scale structure. So we see a range of scales, from galaxies, which are on scales of kiloparsecs, through groups and clusters on scales of megaparsecs, to superclusters on scales of maybe 100 megaparsecs. We measure it largely by using redshift surveys of galaxies, and to date we have redshifts for a couple million galaxies, which gives us really excellent insights into what large-scale structure looks like as a function of redshift. But clustering itself is not enough. There is also a lot of interesting topology going on. coherent structures like filaments and voids and sheets that separate them and so on. We understand why this happens. You may recall that aspherical fluctuation will first turn around and collapse along one axis while expanding in the other two, making things like sheets or walls. Then will turn around on the intermediate axis, collapse into a filament-like structure, and eventually all drain into, again, to quasi-spherical one. So this is the origin of the large-scale topology, although we still don't have good ways of characterizing it. Clustering itself is customarily characterized through two-point correlation function, or equivalently, the power spectrum. The two-point correlation function has a fairly robust functional form. It is well represented, not perfectly, but well, over a large range of scales as a power law with slope of minus 1.8 in three-dimensional space. For galaxies, the normalization given through clustering length is of the order of 5 megaparsec or so. For clusters, it's larger, corresponding to larger amplitude of clustering. And whereas we can easily measure two-point correlation function for any kind of objects, to compare them with theory, we actually have to turn two-point correlation function into a power spectrum. And fortunately, the two are equivalent and they're Fourier pair, so we know how to compute that. Overall, the cold dark matter model fits the data remarkably well over a full range of scales that we can measure through a variety of different methods, which gives us confidence that cold dark matter model is in fact correct. And I should note at this point that it would be very difficult to achieve this if there were no dark matter at all. Generally speaking, objects of different kinds have different clustering strengths that applies to different kinds of galaxies, luminous versus less luminous, early versus late types, and so on, carrying over to the clusters of different richness, and so on. Next, we will talk about large-scale peculiar velocity field, which is a direct consequence of the existence of large-scale density field.